Hi, this is Preston Dye. I will be presenting on passivation of stainless steel. First of all, I'd like to cover a little bit about the surface properties of stainless steel. Oxygen will react with the chromium that is found in stainless steel to create a chromium oxide protective layer. This oxide layer can be strengthened via passivation. The passivation process is shown below. First of all, to overview this process, the material is first chemically degreased. Pickling can remove up to 40 microns from the surface of the material. This is important because it can remove some surface defects and also inclusions that are found in the material that could resist the passivation process. It is important that the surface of the material be completely free of any defects and inclusions so that the passive layer can be complete. Passivation is then performed by being dipped in an acid solution of either citric or nitric or other acids as well. There are several different non-destructive examination methods to determine the properties of the passivation layer. One is X-ray photoelectron spectroscopy. Here, a higher energy X-ray is emitted onto the surface of the material at a certain angle. The electrons are emitted from the surface and are collected at an electron energy analyzer. Here, it is then connected to a detector. This detector displays the chemical makeup of the surface. Using this, you can evaluate properties of your material to verify how much chromium oxide and other properties that are found in your passive layer. Another method for determining the passive layer process, or the passivation process, is via powder X-ray diffraction. And then a similar process determine the chemical makeup of the surface over time. As you can see, some of the chromium oxide is not present in the initial hours after exposure to the solution and is slowly formed. Here is the passivation model. The first phase occurs in the first hour of exposure to the solution, in which the outer iron oxide or hydroxide of the surface is dissolved. The layer below, which is enriched with chromium oxides. The iron in the bulk material is dissolved, leaving a chromium-rich material. These reactions tend to slow over time as the material reaches chemical equilibrium with the solution. On the right-hand side are a few graphs showing different solutions and different rates of change. As can be seen in the lower graph in C, chromium oxide, the very high end, continues to grow over time. Researchers have compared the effectivity of nitric acid versus citric acid. Concentrations of each solution have shown to have an effect on the ratio of chromium to iron, though the optimal concentration is about 10 to 20%. Citrosurf, in this case, has been shown to be able to create a passive layer at approximately 5% concentration, though it has been argued that it is not as effective as nitric acid. Nitric acid is able to continue to increase the chromium to iron ratio until about 30% concentration. Here are a few passivation variables to consider. The potential in passivation. Passive layer in the environment is in constant flux depending on the electrolyte that is in contact with it. The passive layer thickness grows linearly with applied potential. The oxide part of the reaction is driven by this applied potential. As the potential increases, the chromium content decreases. Higher levels of oxidation have been shown at higher potentials. And here on the right-hand side, you can see that as the potential increases, the passive layer, or the passive film, also increases. pH, temperature, and passivation. pH and temperature are both important variables that affect the passive layer. As pH has increased, the dissolution rate has been shown to lower. Basic solutions have shown to create thicker passive layers as iron oxides are more stable in these environments. Temperature has shown little to no effect on the quality of the passive layer. Passivation and critical pitting temperature. Passivation and critical pitting temperature. One study identified the effects of passivation and critical pitting temperature in stainless steel. CPT is the temperature at which the stable pitting is identified, as well as a sudden decrease in breakdown potential. This is an important temperature to know of due to the effects that pitting can have on materials, and by avoiding such temperatures, one is able to possibly prolong the life of their material. Bravo and Newman identified that stable pitting growth can only grow in an anodic salt film. In order to passivate the surface, there is a requisite critical current to overcome the anodic potential. This critical current is temperature dependent. Here on the right hand side, as you can see, as the temperature is increased, the potential required for pitting is lowered. These four graphs show different passivation times, with the upper left being 0 minutes all the way up to D, where it's 24 hours. Some variables to consider with CPT. Passivation improves CPT in three distinct ways: the dissolution of inclusions, the enrichment of chromium oxide in the passive film, and the thickening of the passive film. Chromium oxide and dissolution depth are more critical to the increased performance of CPT, while passive layer thickness plays a smaller role. Dissolution of inclusions reduces the weak sites in the surface of the material. And here are my references.